We now extend what we did for 1D to 2D systems in a very informal way. Typically we spend a whole semester learning a finite element, and we are spending 1 week. So my apologies for this casual extension to 2D. In keeping with the goal for this course, I simply want to capture the conceptual ideas that will hopefully make it a little less of a black box. This slide previews what we will do in this short video as an analogy to the 1D system that we already worked on. So for 1D, this is my governing equation that we would like to solve, and that equation is solved along a line that is my domain. A line because it's a 1D, so I break up the line into elements like that, and then we solve over each one of the elements. So here, if we enlarge one element, then in every node we have a value, temperatures, and at this node we have this TR, and in between here we interpolate, okay, and this is my interpolation equation simply. And then the way we did the method was this assumed solution that we have at the two nodes, we tried to get it as close to the real solution. In other words, we tried to minimize the error, and that gave us these equations to be solved. So if we have two elements here, two elements have three nodal values as my unknown. So these are my unknowns. These are my unknowns, and all these are knowns. Okay, and so then we solve this linear set of equations. That's what we did for 1D. So for 2D, it is exactly analogous. So the equation then has x and y. My domain is now a 2D area, which is broken down. Instead of a line being broken down, area is broken down into triangular elements. And so here is one element, and this particular element has three nodes, and here are at each node, here are the nodal values of temperature, and these all have bars because they are not the true values. We don't know the true values. These are the approximate values, and then again we minimize the difference between these approximate values and true values, and that leads to equation or a matrix just like above, with all the unknowns here, unknowns, and these are all the known things. Okay, so then our problem becomes inverting this matrix to obtain the unknown. So we start from the differential equation, but we end up with the algebraic equation with the unknown. So that is the process that we did for 1D, and it's the same for 2D. So here, this slide is just to make the point that any arbitrary domain can be approximated by a domain with a whole bunch of triangles, let's say. So here in this case, these are the triangular elements. So this is one element, and this element is enlarged here. So the element has 3 nodes, okay, and these are the noded the nodal temperatures. Again, these are the approximate values, and the shading here, the shading is supposed to represent interpolated temperature. So darker values represent different from lighter region. So here is one of those triangles, this one here, with 3 nodes, and these are the temperatures at the nodes. I put a bar there because any calculation using finite element is an approximate temperature. And so these are the temperatures at the 3 nodes of the triangle, and the point is any other temperature inside the triangle can be found by interpolation, and let's see how. So suppose I need temperature at this point, which is, let's say, some xy point. So this point temperature can be found through a set of interpolation. Let's see how. So suppose I join this line. It's kind of hard to see, and so that intersects here on this line. So I do 2 sets of interpolation. First, I interpolate between TR and TS to find this temperature. Then I do another interpolation, but this time between this temperature and this one to get this temperature. So likewise, any point inside the triangle I can find through interpolation if I know these 3 nodal temperatures. Now, what I just described can also be algebraically written this way. So let's say I want, temperature in general for a location xy is given by some alpha 1 plus alpha 2x plus alpha 3y, where alpha 1, alpha 2, alpha 3 are unknown, but t is this kind of a linear function of x and y, as I was just showing by interpolation. So we can find this alpha 1, alpha 2, alpha 3, these guys this way. So for the 3 locations, I can write TR is equal to alpha 1 plus alpha 2 XR, with XR is simply the x coordinate here. This is XR, YR. Likewise, this is XS, YS, and this is XT, YT. And let's try to clean up some of these. Yeah, okay. So those are the coordinates. So for R, I can write alpha 2 XR plus alpha 3 YR. Likewise, TS bar is equal to alpha 1 plus alpha 2 XS plus alpha 3 YS, and TT bar is equal to alpha 1 plus alpha 2 XT plus alpha 3 YT. I am writing this out because it's very simple process. From here, we have 3 equations with 3 unknowns. 3 unknowns, alpha 1, alpha 2, and alpha 3. So we can find these. So if I find alpha 1, alpha 2, alpha 3 from this, and then plug back in here, I'm going to get an expression that looks like this: T equal to something times T R plus something else times Ts plus something else times T. Okay, so this can be written in a matrix form this way: PR PS PT times TR TS T of T, which is a matrix P times a matrix T. Okay, so those quantities that I didn't write out in the last slide, they are given by this, and we get this simply by finding those alpha 1, alpha 2, alpha 3 in the last slide. So this, with this PR, PS, and PT, I can find temperature at any location XY from the 3 nodal temperatures, and this is basically my interpolation function. So notice how this is pretty much exactly the same idea as we did for a line, for example. So if you have two nodes L and R, and we have a value TL and we have a value TR, any point in between can be found through this interpolation, PLTL. Look at the similarity between this equation and this equation here. So this one interpolates between 3 values in a triangle. This one interpolates between 2 values at the 2 nodes in a line element. And in this case, the PL is given by this and PR is given by this. And in this similar way, the PR is given by this expression and so on. So it's exactly analogous. So this is now my interpolation function. So that's really all I wanted to say in terms of the 2D process is quite analogous to 1D. So we also have an interpolation function. And so let's kind of go back and see what we did in 1D. So we have the equation, governing equation over a domain. So let's say a line in 1D, and we broke up the line into elements, and over one of the elements we use the interpolation function between the values that we're trying to estimate at the 2 nodes and the interpolated values in between. That's my solution, and the difference between the solution and the true solution is my error, and we minimize the error to get the equations, and we got as many equations as the number of unknowns. So what it's showing here is for these 2 elements. So for 2 elements we have 3 unknowns, and so for 3 unknowns we have 3 algebraic equations, and we solved. And the process for 2D is exactly the same, that we start from a 2D governing equation over a 2D domain that we break up into triangles. And so this is one of those triangles, and these are the values at the 3 nodes of that triangular element. Then any point inside will have a temperature given by this equation, which is totally analogous to this one. And then again, we minimize error in a very analogous way. And if we minimize the error, we're going to again get a matrix of algebraic equations that will have all of these unknowns, including these and other unknowns. So these are my unknowns, and these would be all known and equal to something that is all known. So by solving this linear set of equations, we solve for all the unknowns, which are the nodal temperatures, and then interpolating between the nodal temperatures, we can get any values within. So that's how the finite element would work for 2D, and it's totally, in a totally analogous way, we can extend it to 3D, where we'll have the 3D interpolation. Thank you.